In the last class, we have derived the Riemann tensor from successive covariant differentiation, and we have seen that it is a mixed tensor of rank 4. Now the same Riemannian curvature tensor can be written in fully covariant form, and it is useful to discuss the symmetric properties of the curvature tensor. So for this, let's proceed as follows. Consider the curvature tensor R alpha nu lambda sigma, and I have to apply lowering operation. So this is a mixed tensor, but I need fully covariant. So here there is one contravariant index which I have to apply the lowering condition and then lower it to the covariant form. Okay, so apply lowering operation with g mu alpha, that is we get r mu nu lambda sigma is equal to g mu alpha r alpha nu lambda sigma. So I have taken a mixed tensor and I am applying the lowering operation to get the fully covariant Riemann tensor. Now this is equal to g mu alpha. Now I have to substitute for r alpha nu lambda sigma. So by definition, the Riemann tensor is partial derivative of the Christoffel symbol minus partial derivative of alpha lambda nu plus Christoffel symbol minus Christoffel symbol rho lambda nu multiplied by Christoffel symbol alpha rho sigma. Okay, so here we know that the Christoffel symbol is given by half g alpha beta partial derivative of g beta sigma with respect to x nu plus minus partial derivative of g sigma nu with respect to x beta. Similarly, Christoffel symbol of alpha lambda nu is half g alpha beta partial derivative of g lambda beta by with respect to x nu plus partial derivative of g beta nu with respect to x lambda partial derivative of lambda nu with respect to x beta. So these are the definition of Christoffel symbols. Now I have to substitute here. Okay, everywhere I have to substitute the Christoffel symbol. Then I'll get r mu nu lambda sigma is equal to g mu alpha as it is, then partial derivative of with respect to x lambda. Okay, so this one I am writing partial derivative with respect to x lambda. Now I have to substitute for Christoffel symbol. Okay, similarly I have to substitute in all other terms also. So first I start with this. Now half g alpha beta partial derivative of beta sigma with respect to x nu plus partial derivative of g nu beta with respect to x sigma minus partial derivative of sigma nu with respect to x beta. Okay, so this is the first term. So the next term is minus partial derivative with respect to x sigma half g alpha beta partial derivative of g beta nu with respect to x lambda plus partial derivative of g lambda beta with respect to x nu minus partial derivative of g nu lambda with respect to x beta. Then the last term. Last term I am writing as it is. Okay, here I am not substituting. Here I am just writing the Christoffel symbol as it is. I am not going to substitute. I am substituting only in the first two terms. Okay, then this g mu alpha which is there outside, I have to multiply each term. Okay, so I'll write g mu alpha multiplied by rho nu sigma alpha rho lambda minus Christoffel symbol alpha rho sigma. So this is our new expression. Here I have to simplify. So you can see that g nu alpha I have to take inside this bracket. That is one step, and this partial derivative is applicable to both g alpha beta as well as this bracket. Okay, so here g alpha beta multiplied by this quantity in the bracket. So I have to apply the partial derivative both to g alpha as well as the bracketed quantity. So you have to be very careful while opening the bracket and substituting. Similarly, the same case in the next term also. This partial derivative is applicable to g alpha beta and also to this bracket. And this g mu alpha I have to multiply to this as well as this term. Okay, so the bracket is ending here somewhere. So I have to multiply to these two quantities, and the third quantity will be as such. Okay, now I am going to substitute. So this will be equal to half partial derivative with respect to x lambda g mu alpha g alpha beta g beta sigma with respect to x nu plus g nu beta with respect to x sigma minus partial derivative of g sigma nu with respect to x beta minus g mu alpha g alpha beta partial derivative of g beta nu with respect to x lambda plus partial derivative of g lambda beta with respect to x nu minus partial derivative of nu lambda with respect to x beta. Now plus, okay, now I have applied the partial derivative to the first term. Now I have to apply the partial derivative to the second term, and I have to keep this g mu alpha g alpha beta outside. Okay, So G mu alpha, G mu alpha, G alpha beta, then partial derivative with respect to x lambda of G beta sigma with respect to x nu plus G nu beta with respect to x sigma minus with respect to x beta G sigma nu minus again G second term also G alpha beta partial derivative with respect to x sigma beta nu x lambda plus G lambda beta with respect to x nu minus nu lambda with respect to x beta, and the last term will be as it is. I'm not going to substitute anything, so it will be alpha rho lambda minus rho lambda nu alpha rho sigma. Okay, so this is R mu nu lambda sigma. Here the partial derivative of this constant will be 0. So when you multiply G mu alpha and G alpha beta, G mu alpha, G mu alpha and G alpha beta is Kronecker tensor of beta mu. Okay, so which is a constant. So when beta equal to mu, it will be unity. So partial derivative of a constant will be 0. Similarly, here also the partial derivative of a constant will be 0. So all those terms will vanish. Here I have to apply the Kronecker tensor. Okay, so I will rewrite half delta beta mu partial derivative G beta sigma with respect to x lambda and x nu plus G nu beta x lambda x sigma minus G sigma nu with respect to x lambda x beta minus G beta nu dou x sigma x lambda plus second derivative of G lambda beta with respect to x sigma x nu minus x sigma x beta, and the last term will be as it is G mu alpha multiplied by rho nu sigma, Christoffel symbol alpha rho lambda, Christoffel symbol rho lambda nu, Christoffel symbol alpha rho sigma. Now I have to apply beta equal to mu. So wherever there is beta, I will replace it with mu. Then I will get R mu nu lambda sigma is equal to 1 by 2 partial derivative of mu sigma with respect to x lambda x nu plus nu mu with respect to x lambda x sigma minus G sigma nu with respect to x lambda x mu minus plus second derivative of G nu lambda with respect to x sigma and x mu plus G mu alpha, Christoffel symbol rho nu sigma, alpha rho lambda nu, alpha rho sigma. Okay. So here these two terms will get cancelled. Okay. And similarly, here I can multiply this inside. Then I can write R mu nu equal to half of with respect to x lambda x nu with respect to x sigma x mu minus x sigma x nu plus, now here I have multiplied G mu alpha and this one because there is alpha here. Okay, so the final product will be Christoffel symbol, alpha and alpha will get summed over. So I'll get mu rho lambda. Similarly here also there is alpha. So alpha and alpha will get summed over. I'll get Christoffel symbol mu rho sigma. So plus rho nu sigma, rho mu lambda, rho lambda nu, rho mu sigma. Okay, now from here I can take out G rho alpha from this term. Okay, common outside I can take. So let me take and show you what are the remaining quantities. So this can be 1 by 2 multiplied by x sigma x mu plus, I'm going to take out G rho alpha. Then the remaining quantities will be rho mu sigma alpha mu lambda minus rho lambda nu alpha mu sigma. Okay, so initially it was G mu alpha, now it is G rho alpha. Okay, this is the fully covariant Riemannian tensor. Okay, so I'll just write once again. R mu nu sigma lambda is equal to 1 by 2 partial derivative of G mu sigma with respect to x lambda x nu plus partial derivative of nu lambda with respect to x sigma and x mu minus partial derivative of g lambda mu with respect to x sigma and x nu minus partial derivative of g sigma nu with respect to x lambda and x mu plus g rho alpha, Christoffel symbol rho mu sigma, alpha mu rho minus Christoffel symbol rho lambda nu, alpha mu sigma. Okay, this is the fully covariant Riemann tensor. Okay, so once you get the fully covariant Riemann tensor, now let's see what happens when we interchange the last two indices. So here sigma and lambda. Let's see what happens when you interchange the last two indices. Okay, now we can write R. I have to interchange the last two indices. Okay, so initially it was sigma lambda. Now I have to write lambda sigma. So R mu nu lambda sigma is equal to, so wherever there is lambda, I'll replace it with sigma, and sigma I'll replace it with lambda. X sigma x nu plus with respect to x lambda and x mu minus partial derivative of g sigma mu with respect to x lambda x nu minus partial derivative of g lambda nu with respect to x sigma x nu plus g rho alpha rho mu lambda, Christoffel symbol alpha mu sigma minus, if you compare this with the original fully covariant Riemann tensor before interchanging, then this is equal to minus r mu nu sigma lambda. Okay, so when I exchange last two indices, I am getting negative of r. Now let's interchange the first two indices, that is mu and nu. Okay, then I'll get r nu mu sigma lambda is equal to half of, so wherever there is mu, I am going to replace it with nu and nu with mu. So g nu sigma x lambda plus g mu lambda with respect to x sigma and x nu minus g square lambda mu, sorry, partial derivative of g lambda nu with respect to x sigma x mu, then sigma mu with respect to x lambda x nu plus g rho alpha, Christoffel symbol alpha nu lambda okay. Now if I compare this equation with the original equation for fully covariant Riemann tensor, then this is equal to minus r mu sigma lambda. So if I interchange last two indices, then I am getting negative. If I am exchanging the first two indices, then also I am getting negative. Now what I am going to do, I am going to interchange pairwise. So I have mu lambda sigma. So I am pairing these two and these two. Now I interchange the pair as it is. Okay. Then I will get R lambda sigma mu is equal to plus G sigma mu minus with respect to X sigma G rho alpha mu lambda minus rho lambda nu alpha mu sigma. Now if you compare this with the original one, then it is the same. There is no change. So if you interchange pairwise lambda sigma and mu nu, then I'm getting R mu nu lambda sigma as it is. Okay, so if I interchange the last two indices, then I'll get negative of the original one. If I interchange the first two indices, then I get the negative of the fully covariant Riemannian tensor. Then if I interchange pairwise, that is mu nu and lambda sigma pairwise, then I'll get the Riemann tensor itself. So I will write this in a particular notation. Thus, the fully covariant curvature tensor obey the following symmetric properties, that is R mu nu lambda sigma. So this square bracket means anti-symmetric, minus R mu nu lambda sigma. Then R mu nu lambda sigma is equal to minus R mu nu lambda sigma. So with respect to last two indices and first two indices, it is anti-symmetric. Now if I interchange pairwise, that is mu nu and lambda sigma, then I get R mu nu lambda sigma, which means pairwise it is symmetric. So this means that the curvature tensor is anti-symmetric in interchange of last two indices and is also anti-symmetric in interchange of the first two indices, and finally symmetric in interchange of pair of indices. Okay. So that So these are the properties of the fully covariant Riemann tensor. Now we have to find the Bianchi identities in terms of the fully covariant Riemann tensor. For that, consider R mu nu lambda sigma. Okay, so by definition it is half of partial derivative with respect to x nu x lambda g nu lambda minus x nu with respect to x mu and x lambda plus g rho alpha Christoffel symbol So this is by definition R mu nu lambda sigma. Now I am going to cyclically permute the last three indices. So here the last three indices are nu lambda sigma. Nu lambda sigma. I am going to do the cyclic permutation of last three indices. Then, so let this be equation number 1. Now I am going to do the first cyclic permutation of the last three indices. Then we get R mu sigma nu lambda. Okay, so here I have done first permutation. So sigma nu lambda is equal to g mu lambda with respect to x sigma x nu g sigma nu with respect to x mu g mu nu with respect to x lambda minus g sigma lambda with respect to x nu plus g rho alpha minus let this be equation number 2. Now I do one more cyclic permutation. Then I'll get R mu lambda sigma nu. So this one more cyclic permutation with respect to last three indices only. Okay, last three indices. Mu we are not touching. Mu will be there as it is. Now g mu nu plus g rho alpha Stoffel symbol rho lambda nu minus okay, so let this be 3. Then I am going to add equation 1 plus 2 plus 3. So I'll get R mu nu lambda sigma plus r mu sigma nu lambda plus r mu lambda sigma nu is equal to 0. Similarly, if I take the covariant differentiation of this equation, then I'll get plus is equal to 0. So here I take the covariant differentiation of the fully covariant Riemann tensor and then cyclically permute with respect to last two indices only. See here, gamma delta is common, which means cyclic permutation with respect to last two indices. And then add everything, you will get 0. So this I can write in another notation like R gamma delta. No, I am only changing. See here, sigma lambda, alpha sigma. Only the last two are getting changed. So that I can write as sigma lambda. Then semicolon represents covariant differentiation with respect to alpha is equal to 0. So this is another notation for this equation. Here semicolon represents covariant derivative. So there is one more notation for the same equation. Covariant derivative with respect to alpha r sigma lambda. So these are the changing ones and gamma delta as it is. This is equal to 0. So these are the Bianchi identities. Okay, so this is the differential identity. And this one is the algebraic identity. Bianchi identity algebraic and Bianchi identity differential. Okay. Bianchi identities for the fully covariant Riemann tensor. So for today's class, we will stop here. So in another 1 or 2 classes, we will wind up the tensors and we will go to the other topics.